Got it. Okay. So yes, I'm going to talk about confining hidden sectors at the LHC and beyond. This is work done in collaboration with a bunch of people. The first paper with Pedro Schwaller and Andreas Weiler, who are both in Germany now, and then various people like Carlton in my group. You know, the thing with Zoom chats, it's hard to see the audience, obviously. You can put in questions in the chat and I may or may not see them. I'm not sure how well that would work, but if you have questions, I'd be more than happy for you to interrupt anytime and shout out questions. Okay, so let me start. Why am I going to talk about this? Why should we care about confining hidden sectors? And the first is the hierarchy problem, right? So probably all of you have been in a talk where the hierarchy problem is what's talked about in the first slide, although maybe less so now. But right, we have this quadratic sensitivity to new scales for the Higgs mass from the top loop and for other things. And so the famous solutions are, they all involve new states that couple to the Higgs. For example, supersymmetry has scalar top partners. Can you see my pointer?
Yes, I can see.
Very good, thank you. Supersymmetry has these scalar top partners that couple to the Higgs, or composite Higgs models have fermionic top partners that couple to the Higgs, and you get some minus sign to cancel the quadratic divergence in the standard model. These, of course, are not hidden sectors. These things carry color. They talk very well to the standard model, but these things, of course, also haven't been discovered, and there are now very, very strong bounds on these things. And so the question is, do they really need to be colored? Do those things need to talk to the standard model? And the answer, of course, famously is no. But you still do need a factor of 3, right? You need to have 3 colors or some kind of factor of 3 in this loop in order for you to still properly cancel the quadratic divergences and solve the hierarchy problem. And so so-called models of twin Higgs or folded SUSY, these top partners do not carry standard model color, but they carry some other color, right? And so because they have this other quantum number, they still get the factor of 3. And there's various other clever things that happen in these kinds of twin Higgs or folded SUSY models. And so they have a twin color. These models have a twin color, and the scale of the twin color is not so different than the scale of standard model color. So it's around the GeV scale or maybe slightly higher. All right, so that's motivation number 1. Motivation number 2 is dark matter. Also, probably many talks you've seen start with dark matter exists. We've seen it in the sky. We haven't seen it in the lab, especially for these plots at the bottom are searches for WIMPs. And there have been many searches for WIMPs that haven't found anything. And so maybe WIMP is not really the right paradigm. And so I want to talk about a different paradigm that's not the weakly interacting massive particle, which is asymmetric dark matter. And asymmetric dark matter starts with this, let's call it a coincidence, this fact that the dark matter relic density, the energy density in the universe in dark matter, is a factor of 5 bigger than the baryon density of the in the universe. Factor of 5 is kind of like an order 1 number, and generically these things could be orders of magnitude different. It's hard to really come up with an explanation of why these things are so similar, only a factor of 5 apart. In particular, in WIMP models, you don't get this. It's sort of an accident that these two things come out similar. And so, okay, let's think about how we can maybe get this, right? So the energy density is, I've ignored some constants, but it's the mass times the number density. And so if we look at this baryon, the standard model side, we should understand everything here. So the mass of the mass of the ordinary baryons is the mass of the protons, and it's controlled by QCD dynamics. Those are complicated dynamics of dimensional transmutation, but we understand how that works pretty well. On the other hand, the number density of baryons, we don't have really any idea how it works. We have a name for it. We call it baryogenesis. There's something that gives you more baryons and antibaryons, but we don't know what the mechanism is in nature that does this. Okay, so the first thing we can try is maybe whatever controls the asymmetry of baryons also controls the asymmetry of dark matter. And so these number densities come out roughly the same, and you get the same dynamics. And so there's some dark matter and anti-dark matter, and the asymmetry of dark matter to anti-dark matter controls the number density today. And so this is actually a very old idea. It goes back to Newsonoff some 40 years ago, roughly. And there have been many papers sort of more recently, and this is an extremely incomplete list. There are many more of this idea. And all of these papers, they typically give you that the number density of dark matter and the number density of baryons are similar, are the same order of magnitude, but they don't tell you anything about this, right? In order to explain why the relic abundances are the same, you also need to explain why the masses, the mass of dark matter and the mass of the proton, are roughly similar. And so the question is, can you do both? And so if I go back to this sort of flowchart, well, if this dark matter mass is somehow controlled by some similar QCD-like dynamics, and then you can somehow make these two QCD-like dynamics similar, then you can more properly succeed in explaining this coincidence of dark matter and baryon abundances. And so this is an idea, I'm going to follow this idea by Yang Bai and Pedro Schwaller from 10 or so years ago, which is that you have a new dark color force, dark QCD, with dark quarks. And just like the baryons in the standard model are stable because of some accidental baryon number, you're going to have some baryons with mass, which are also stable, and they are the dark matter from the dark QCD. Their mass is roughly the confinement scale, just like in the standard model. There's also some massive field that talks to both, that talks to color and dark color, and it decouples at some mass, which is large compared to the dark confinement scale. And so the trick that Bai and Schwaller did was you look for models with perturbative fixed points, such that they both QCD and dark QCD run to this fixed point at scales above this M, and then once you decouple these scales, they both run towards confinement, and they run roughly from the same place, and so you can get the masses to be similar. So this is a sort of picture in renormalization group space and in coupling, so energy on the horizontal axis and coupling on the vertical axis. So you want both dark QCD and standard model QCD to run to some fixed point, so then it's sort of independent of your initial conditions. And then at some scale M, you decouple a field that is that sees both kinds of color, and so then they both run to the confinement scale. And the ratio of these confinement scales, which is roughly the ratio of dark matter to protons, is something like this in terms of things. And these B's and alphas are all calculable in this setup. And so one example is the alpha star is the value of the fixed point are here. Then the mass where this starts to run up is set by the proton mass. You run this up, and that mass is 3.5 GeV, and the mass of this heavy state is 870 GeV. So this sort of example will guide me in what I'm going to do later. I'm going to talk about sort of TeV-ish scale mediator masses and few GeV-ish scale dark bound states. Okay, and then one more thing that's interesting about this dark matter story of Bai and Schwaller is that you can indeed co-generate the baryon asymmetry. This field phi, this field phi is the field that couples to both QCD and dark QCD, which means if you set up the weak quantum numbers appropriately, you can write down this Yukawa coupling. And so then if you give phi some kind of asymmetry, when it decays, it will share its asymmetry 1-to-1 exactly between quarks and dark quarks, so standard model quarks and dark quarks. And then dark matter is kind of like a proton or a neutron, so the cross-section, the interaction cross-section between these things is pretty big, which is maybe interesting. You can do some things with sort of galactic scale dark matter things and solve these kinds of problems that lambda CDM maybe doesn't do. All right, so let me summarize sort of the general picture is that we have the standard model sector or the QCD sector, and then we have the dark sector. The vertical axis is mass or energy, so the dark sector is a little bit heavier, but not a lot heavier. you have this mediator, so it decays and it sends asymmetries to both sides. You have the dark baryons, which are stable, but they can annihilate, and so the symmetric component will annihilate away. You also have the dark mesons, which will decay back to standard model stuff. All right, so let me pause there if there are any questions before moving on to phenomenology. Okay, so let's talk about phenomenology of colliders. So what do we have? We have a confining SUN gauge group with NF flavors. So we can talk about dark quarks, dark gluons. The confinement scale is something like 1 to 10 GeV, let's say. And then we have all the usual states, just like in QCD, at the confinement scale. So we have the dark proton, that thing is stable. We have the dark pion, which decays on collider timescales, as I'll explain in a few minutes. And then the rest of the dark zoo, right? Rhos and A's and F's and all the usual things we talk about. And then the mediator, right? So I briefly mentioned a possible scalar mediator. So we'll take the mediator to be heavy compared to the confinement scale. And it will be something that couples to the standard model and to the dark sector. And so that way we can produce the dark sector via this mediator. So the one example is the one from the Bi-Schwaller model, which is a scalar which carries color and dark color. So this is you can generate some diagram like this. This is called the bifundamental mediator, if you like, because it carries fundamental charges under color and dark color. But there's an even actually slightly simpler mediator that you can talk about, which is the standard hidden valley type model, right? So the hidden valley framework of Strassler and Zurich is that you have a bunch of light states around and then some heavy mediator. And in this case, the heavy mediator is some vector that couples to some quark current and some dark quark current, and you can produce these dark quarks in this way. Okay, so if you produce dark quarks at, let's say, the LHC, you smash ordinary stuff together, you produce dark quarks, right? So what happens when you produce dark quarks? It's analogous to what happens when you produce quarks at a lepton collider like LEP or some E+ E- machine, right? So the initial state is a singlet under the confining, the strong force, and the final state is not, and so you get showering and hadronization, right? You get jets. And so, especially if these Qs are very energetic compared to the confinement scale, you get jets with large multiplicities going roughly in the same direction. And so if you pair produce Q, you end up with 2 back-to-back dark jets. And then what happens here, right? What happens to all this stuff? If these were invisible, right, this would look like a missing energy event. It's no different than the ordinary missing energy searches, but that's not what happens. Right, and I mentioned this earlier, we have these pions, and they decay. They decay on collider timescales. And why do they decay? Well, the same operator we use to generate the asymmetry, right, this UCAL coupling, which couples a scalar to a dark quark and a quark, it generates the asymmetry, allows you to draw a diagram like this, which is Q and Q bar on one side and dark Q and Q bar on the other side. And so because the phi is very heavy compared to all these other states, we can just integrate it out, and it's this 4 Fermi operator, and then Q and Q bar is a dark pion, right? So this operator is going to mediate the dark pion decaying to quarks. If instead we're doing the Z dark model, we can do the exact same thing. We have this diagram, we integrate out the Z dark, we get this 4 Fermi operator, becomes dark pion decay. And then we can compute the decay length, right, just from the dark chiral Lagrangian plus this 4 Fermi operator. And this is the formula. Or if you want to figure out the lifetime, the scale, again, is something like 10 centimeters times, of course, a bunch of constants we don't know. But if you set them to reasonable values, you get something like 10 centimeters. And so if I go back to my sort of cartoon event display, I have my dark jets. But each one of these dark pions, if it's made only of pions, each one of these dark pions will decay at some point somewhere in this as it travels. But they all, of course, decay at different points, right? There's the usual exponential decay law from quantum mechanics. Just because something has a lifetime of X, it doesn't mean it will live at time X, but it samples from an exponential distribution. And so we've called this thing an emerging jet. because at very short distances, it's totally invisible. And at very long distances, it looks essentially like an ordinary jet. But in between, it emerges. It goes from total darkness to popping out full energy of a jet out of the vacuum. And so that's the cartoon that I drew. But actually, as I'll talk about in detail more, the experimentalists have taken this up. And so here's an actual simulation of an emerging jets event at Atlas. And so you can see the several displaced vertices inside the jet cone. So as far as I know, there's only one easily reconstructible emerging jet in this event display, which is here. But maybe there's other ones that are harder to see. Of course, doing this professionally is much harder than doing this as a phenomenologist, but they have begun to attempt this. And so for us, we needed to simulate. We need to simulate these kinds of events, and certainly if you want to convince experimentalists to do a search, they also will ask you for tools to simulate these events. But luckily, dark showering and hadronization was already in Pythia as of 2010, 2011. So long before we started doing this. We had to modify Pythia to include some effects that weren't initially included, but those are also now included. So if you just download Pythia out of the box, it will do dark QCD, no problem. And so what happens when you try to do this at a collider? If you pair produce this phi, this mediator, right? The mediator carries color. It's a scalar colored object, so you can only pair produce it. And then each one decays to Q bar, Q. And so the final state is two ordinary jets, two QCD jets, this Q and this Q bar, and two emerging jets, which are the capital Qs. And the production cross-section for this process is similar to stop quark production, right? It's a colored scalar. So it's a few times the cross-section of top production, which is, easily lookupable at even NLO. And so if the mediator is 1 TeV, the cross section is something like 10 femtobarn at LHC 14. There's also this Z dark mediator. In this case, you don't get the additional standard model jets. The final state is only the two emerging jets, and the cross section depends on these couplings, which are free parameters. So it's not fixed like the other one. I'm going to spend a while talking about benchmark 1, and then I'm going to come back to benchmark 2 in a bit. Okay. So we wrote this paper some, I guess, 8 years ago now. Geez, it's a long time. Proposing this search, and we said at the LHC you could bound sort of this region in. So the horizontal axis is mediator, and the vertical axis is the lifetime of the dark pions. There's one more parameter, of course, which is the mass of the dark pions, and a bunch of parameters associated with showering, but these are the two most important. And we tried to get experimentalists to do this search, and in fact, they have. So as I said before, Atlas is working on this. CMS has even published something. So CMS has published a search for a new particle decaying to a jet and an emerging jet. I guess it's JHEP in 2019. And so what did they do? How did they try to discriminate this from background? Of course, the background is complicated and difficult to characterize, but what they use to try to discriminate it from background is the average transverse impact parameter. So you figure out the impact parameter of the tracks inside your jet. So QCD peaks at very low values, just essentially 0 plus or minus the resolution, while the emerging jet peaks at much higher values, right? This is the log of the impact parameter. And the other one is the momentum fraction below a given displacement. So you count up all the tracks that are displaced by a certain amount, and you ask what fraction of the momentum of the jet are carried in those tracks, and that is going to peak around 1 for the or you flip it. So QCD is going to peak around 1. What fraction are below a given displacement, while the signal is going to peak around 0.
Excuse me, may I have a question?
Please.
So can you go back to about 5 page before for this one.
Okay.
So I'm wondering what kind of situation one QCD jet and one emergent jet will merge to each other.
Oh, good question. That seems hard to engineer. I mean, I suppose if one QCD jet and one emerging jet, right? So there's conservation of color, right? So at the sort of dark parton level, you're always going to produce two dark quarks, right?
Yeah.
And so in order to get only one emerging jet, well, you could lose one, right? If one of the dark quarks just goes straight down the beam line, or if they're merged, right? If the two dark quarks are pointing in the exact same direction,
Yeah.
which in this model you'll get by accident every once in a while. But if you boost the phi, you merge one of the jets and the dark jets. You don't merge the two dark jets, so that's rare. So I have never considered that before. Other than by accident, I don't see a way you can do it.
Okay, I see.
Yeah. Okay. So I take it back. I do have a way, not in this model, but in this model, right? If
Yeah.
you boost the Z, right? So you produce a Z plus a single jet, then these two will merge, and then that will do it.
Okay. See. Okay. Thank
No,
you.
thanks. Good question. Other questions? Okay, so this is the limit that CMS published. Looks, the shape is the same as ours, and the limit is actually a little bit stronger, because they use 1/6 as much luminosity as we projected. So we were, I guess, a little bit conservative, but it looks roughly the same. So it's very, very cool that this thing that we did as very naive theorists, when the professionals did this, they got more or less the same answer. And of course, you haven't heard about this, or it's not been big news, so they only set limits. There's no discovery, but this search program is ongoing. And in particular, if you open this paper, they have, as usual, they have many signal regions where they have different cuts on their search variables. And I looked at this and I see that the expected number of background events in signal region 2 is 32, and the observed is 47. So that seems like some kind of excess. So a friend of mine worked on this for CMS, and me, a dumb theorist, asked him, should I be excited about the 3 sigma excess in set number 2? And Ted Kohlberg, who's an experimentalist who's not dumb, he said, well, he did not throw all the cold water on me. He said, I think it'll be interesting to repeat the analysis next year with close to 10x more data. Of course, next year is now 2 years ago, but they do have 10x more data, and they are working on it as far as I know. So someday soon, if this thing is real, we will see exactly what's going on with it with a lot more data. All right, and then Atlas has a team working on it, including a bunch of experimentalists at Carleton. I'm told that their run 2 analysis will come out soon, but it's hard, it takes a long time. So there's no public information, but I have seen plots from students and postdocs that look something like this, and so I do know that they're working very hard on it, but as yet they have not published it, don't have anything public. And then LHCb, we pointed this out in the first paper. LHCb is actually pretty well designed for this, because it's designed to do tracking of displaced objects. Like B mesons are exactly this, and it has amazing tracking. Of course, LHCb has limited angular coverage, geometric coverage, as compared to CMS and Atlas. It's only a little forward slice, but still, it has some very strong advantages. And so informally, I've talked to some LHCb people that seemed interested in this, but none of them have reached out to me in the last few years. So I don't know if it's ongoing. But if you happen to be an LHCb member and are interested, please let's get in touch. I think LHCb could do very well at this, and it would be very complementary to what the other detectors are doing. All right. So the rest of the talk is going to be a potpourri. I'm going to talk about a bunch of random things, sort of related. But not really related to one another, just related to the first part of the talk. So I guess let me pause, ask if there are any questions before I go on to the potpourri round. Okay, so our work and the work of various other theorists talking about different kinds of scenarios with long-lived particles has spawned this LLP community, which is a joint effort between experimentalists and theorists to try to figure out what can be done in practice. How can it be done the best way? How to optimize the searches, optimize the person power on the experiments doing these kinds of things. And this group is now having its 13th workshop this summer at CERN. And I think this one will be hybrid or in person, which it hasn't been for a while, but they've been doing these meetings once or twice a year for quite some time. And this group has generated, you may have seen on the archive, this white paper searching for long-lived particles beyond the standard model at the LHC. So it's this 300-page white paper. And it includes a chapter on dark showers, which Pedro has given this wonderful logo to, which emerging jets are an example of. And so there's this chapter 7 of this white paper is the dark showers chapter. So there's we did a lot in putting together what has been done, but I think the upshot of this is that there's lots of work to do, especially getting experimentalists and theorists working together to work towards a thorough experimental program of covering, model space and all the possible weirdo things that could be out there involving displaced particles or long-lived particles. And so this followed on to some SNOWMASS activity, right? So this is somewhat more recent. It's from early last year. There's a theory, phenomenology, and experimental avenues for dark showers. So this is dark showers only, not all possible long-lived particles. So there's more progress along what can be done and what the experimentalists what questions the experimentalists have that we can try to answer as a theory community as well. All right, so another topic is this idea of future detectors. So the LHC, of course, has ATLAS, CMS, LHCb, various others. But this idea of long-lived particles means that if you put detectors further away from the LHC interaction point, maybe you can discover these long-lived particles with dedicated detectors. And so these are the names of some of the proposed detectors and experiments, although some of them are more than proposed. So Modal is taking data right now. It's and Phasor is under construction, so it's approved and it's being built as we speak. And these other ones are in R&D stages. They have various prototypes at different stages, but the full detector is not yet built. And so I started looking at this first in 2015, thinking about SHIP. So there's this SHIP white paper, and there's a section on emerging jets. And then in 2018, thinking about Methuselah, which is big in Canada. A lot of the proponents are in Canada. And so we did this quantitative study for the Methuselah physics case. How well does Methuselah do as a function of lifetime? And we can compare to ATLAS and CMS. But this left open the question, right, is that I, as a theorist, am not a member of any of these experiments. So maybe one should do a comparison, right? Which one is really the best? And of course, which is the best is a very subjective question, but we can ask the more specific question of which is the best to find the emerging jet scenario. And so that's something I tackled with my students, Paul Archer-Smith and Dylan Linthorn. And so the first thing we want to do is compare the geometry of all the different detectors. And so I put up the names of 7 or 8 detectors on the last slide. Here, let me talk about 4 of them. And right, if I do the usual spherical coordinates for the beamline and ask what is the reach of what is the geometric coverage of these detectors? So ATLAS and CMS would be sort of, they cover this whole thing except for like a tiny slice near the very right side. But these things are much further away, so they don't cover quite as much. And so this is the geometric acceptance in theta phi, where theta is the angle off the beam. And so you can see they're all very different. And so they're going to be sensitive to different physics. Some of the other ones, the ones that are not on there, are going to be tiny in this plot. So the other ones are very forward, very far away, and so they cover a very, very small angular acceptance in these coordinates. And so for now, let me focus on these 4, and then we can compare them. So for example, we can ask, what is the limit they will place on the cross-section as a function of lifetime for a fixed masses? So fixed mediator mass and fixed dark pion mass. And you can see they all have roughly the same shape, right? If the lifetime is too short, they have the stuff never gets to them. If the lifetime is too long, this mostly passes through. And so they all have a minimum, an optimal sensitivity, and the optimal sensitivity is going to be roughly how far away they are from the interaction point. And so you can see that the optimum sensitivity is different for the optimum sensitivity point is different for the different detectors. And you can also see that at long lifetimes, sort of you should push for Methuselah, but at intermediate lifetimes, Anubis, and at short lifetimes, we've got Alex. And so they are very complementary. And actually, this is maybe a case that you should be building all of these detectors. Similarly, it's that you can fix the cross section and vary the pion mass, and still the lifetime is on the horizontal axis. And again, you see that they're very different. Mostly the lifetime is the most important thing, but you get different expected constraints or expected limits for the different experiments. Okay, but then Phaser is actually being built. So let me see if there's anything I can do about Phaser. So Phaser, it turns out there's very little acceptance for the usual pair production of the mediator. But if this mediator has a Yukawa coupling, there's also the T-channel production of emerging jets, right? So I run time left to right here. And so this is T-channel production. The phi doesn't go on shell. It's proportional to these 2 Yukawa couplings, which a priori you have no idea what they are. But if I just make some assumption about them, some reasonable assumption, at Phaser, I do really well. I get a lot of sensitivity for this T-channel production, much more certainly than for the X pair production. And that's because this T-channel process it's like Rutherford scattering. It tends to go forward, which is exactly where Phaser is. So there is some sensitivity for Phaser to this process. All right, so another topic, and that's triggering. So very often when I would give this talk in front of experimentalists, they would ask, how the heck are you going to trigger on emerging jets, right? And so taking a step back, for those who don't know what a trigger is, the LHC collisions are extremely high rate, and so the experiments can't write down all the results. They can't use all the hard drives in the world every second. And so they have to have some fast way to reduce the data rate from order 10 megahertz to order 1 kilohertz. So it's an enormous reduction in rate. And so the triggers, they look for things that are high energy. So a lot of energy, a lot of jets, leptons, etc. And they're definitely not designed to look for emerging jets. And this is important, right? Because the trigger throws away the events that it doesn't find interesting. And once the events are thrown away, they're gone forever. So if you're not triggering on your new physics, you cannot discover it. And so, of course, CMS has a published emerging jet search. They solved this problem. And the way they solved it is they used high mass mediators. So they used the mediator, the phi mediator, the scalar. And so they have these 2 extra jets, plus the mediator is very, very heavy. So there's an enormous amount of total energy in the event, which makes triggering very easy, right? You can trigger on high energy jets and total high energy events. But we don't know the theory of nature. Nature could have an emerging jet theory with the Z prime mediator where there are no extra jets, and it could be light, right? So it could be this Z prime could be much lighter than 1 TeV. And so we want to see if we can try to trigger on that. And the first trick we use is a old trick known to these authors, or first explored by these authors in terms of dark matter, right? So when you want to look for dark matter, well, dark matter is invisible, you can't see it. But if you radiate a gluon and the gluon is against nothing, this is the so-called monojet strategy, and that's how you look for dark matter. And so you can do the same thing here. You can radiate a gluon or a photon or a W or a Z or whatever. And then your event topology looks like this, right? This is Mercedes topology, if you like, where you get a hard jet and then two emerging jets going in closer to the same direction. So if this thing is sufficiently hard compared to the Z mass, then exactly the question that was asked before, you merge the two emerging jets and you get one emerging jet. But what this does is it adds energy, right? These emerging jets are now more likely to be boosted, so they have more energy, plus you can trigger on this ISR jet itself, which was the original strategy proposed in these papers to look for invisible stuff. And so I published this with my student Dylan a couple years ago. And first you can look at what happens to the trigger efficiency when you do this. And we haven't changed the physics. All we've done is, so this LO plot is blue. This LO plot says, leading order says you just simulate this process out of the box with very low mass C primes, and you get extremely low trigger efficiency. Now you don't add new physics, you just simulate more physics, right? You simulate the radiation of one jet or simulate the radiation of two jets. So that's the green and orange, that's these two. So those already significantly raise the efficiency, especially for masses below 500 GeV. Or you could simulate the radiation of a photon or an electroweak gauge boson, which also raise the efficiency. And so this is using the HT trigger, so the total energy. This is using the missing energy trigger, but it's the same idea. Now you may ask, well, doesn't this reduce the rate, right? So the rate of radiating jet is some alpha S, the rate of radiating a photon or a WZ is some alpha, or maybe even smaller for the electroweak gauge bosons. So probably the better thing to plot on the vertical axis is not the efficiency, but the rate. So the cross-section times efficiency divided by the cross-section times efficiency at leading order. And so then the QED and the electroweak radiation maybe don't help you a whole lot, but still the jet radiation does help quite a lot, especially at low masses. You can get orders of magnitude improvement in rate just by simulating the extra jets. And so this is using the missing energy trigger for some model with relatively long-lived dark pions. If you go to shorter-lived dark pions, which is what we called Model B, missing energy trigger doesn't work, but the HT trigger does. And now you do even better still, right? So here in this gray region, effectively the cross-section, the leading order cross-section is 0. So the denominator is 0, so we couldn't really even simulate anything. So you get, in some sense, an infinite improvement for very low mass. And then the other thing we studied with Dylan, I didn't have the reference here, but yeah, the other thing I studied with Dylan is can you design new triggers using some clever techniques that will look specifically for emerging jets. And this is a little trickier, right? Because you have to estimate the background for these triggers. You have to know that, if you can't just look for jets at low energy, right? Because then you'll get infinite number of QCD jets and the whole trigger will fail. So you have to find a trigger strategy that rejects the background, or has to do it very, very quickly. And so this is what we settled on. Well, first we note that the tracker has the largest number of decays. So the purple line is the decays inside the inner tracker. So that's the innermost layer of the detector. And regardless of the lifetime, the innermost layer of the detector has the most decays. So you should use the tracker. And the way the tracker works is a bunch of layers that look for energy deposition. And the way it works under standard operation is they sort of stitch together all these energy depositions to form a track, a line, through geometric space. But our suggestion was, what if you just count hits, right? So if you have an invisible thing, it won't leave any energy in the things closest to the inner part, but it will leave energy on the outside. So what if you just count the number of hits in each layer and watch it change, watch it go up, which it shouldn't do for a QCD-like event. And this is useful for a trigger because it's fast. You just count. You don't have to do any geometric reconstruction. And so we threw this all into some machine learning. This was Dylan's idea to take the number of counts in each layer inside a jet cone and throw it to machine learning, and then have the machine tell apart the signal from the background, and it does a great job, right? The signal is in green, the background is in blue. You can see if you put a cut somewhere like here, you get enormous background rejection. Of course, the downside of machine learning is you don't know what the machine is doing, right? You don't get physical understanding of how the machine is discriminating signal from background, but that's fine, right? For the trigger, who cares? The trigger's job is not to give you physical understanding. The trigger's job is to write down the important events. And then you can do your offline analysis and get as much physical understanding as you are capable of. And so you need to reject QCD at a rate of about 1 to 1,000. And when you do that, so something like 1 in 1,000. And so this is the ROC curve. I don't know why it's called ROC, but or ROC curve, receiver operator characteristic. But anyway, it's where do you place the cut such that this is the background rejection on the vertical axis. So the harder you cut, you get less signal, but also more background rejection. And so you can still, even for this MZ prime to be relatively light, you can get efficiencies of order 10 to 30%, depending on the lifetime. And the other downside for machine learning is that, well, you have to pick a model to train your machine, right? But we don't know the model of nature. So how can you possibly train the machine? And so what we did was we tested a bunch of different models. We trained the machine on one model and then asked how well does it do on other models. And so that's sort of this matrix. So the diagonal elements of this matrix are, if you train on model A and you test on model A, how well does it do? The values, 1 is a perfect discriminator and 0.5 is a coin flip discriminator. And so, but the point is that the values across the horizontal are roughly constant, right? So there's this universality of training, at least in these emerging jet type models. I don't know if you go crazy in model space, but for emerging jet type models with reasonable variation, you get this universality. One second, sorry. All right, here's another topic, which is flavor constraints. So I wrote down this UCal coupling. This is what, in at least for the case of the scalar mediator, this is the UCal coupling that gives you the decay of the dark pions. And this is a coupling between dark quarks and quarks. But of course, standard model quark, I have to define what I mean by that. And in particular, this is a vector in flavor space, right? If it's a down type quark, it could be D, S, or B. And so with this process, you can draw loop diagrams, which mediate flavor changing effects. And flavor is, of course, extremely consistent with the standard model up to some very small anomalies and extremely well constrained. So for example, you can mediate an electric dipole moment of a quark, or you can mediate flavor changing neutral currents, delta F equals 2 neutral currents, via loops in these kinds of processes. And so let me talk first about electric dipole moments. So electric dipole moments are CP violating physics, but there could be CP violating physics in this Yukawa coupling, right? There's no reason for the phase of this Yukawa to be real. And if you have CP violating physics at the TeV scale, it's almost always excluded by EDM, by electric dipole moment bounds. But it turns out it's not in this theory. So this is a paper with a postdoc at Carleton. And so the way you calculate electric dipole moment, you can compute quark-quark photon or gluon for chromoelectric dipole moment. And then you take the imaginary part of this amplitude to get the electric dipole moment. The real part is the magnetic dipole moment. But for the one loop diagram, you just put in the Yukawa couplings that appear here and here, and you get something like this. And this is a complex number times its conjugate, which obviously has 0 imaginary part. So that's neat. The one loop contribution to the EDM vanishes. And actually, then you can enumerate all the possible 2 loop diagrams, and the same thing happens. All the possible 2 loop diagrams turn out to be real, and they do not contribute to EDMs. So the leading contribution is a 3-loop. We certainly didn't calculate the 3-loop diagram, but you can estimate it. And the important factor is this one, the loop factor cubed. And you get something like this, while the limit is 10 to the minus 26 ECM. So we're a factor of 1,000 away from the limit. And so for TeV scale mediator. And so the electric dipole moments do not constrain this model at all, even though you do have TeV scale CP violating. All right, but what does constrain this model is the delta F equals 2, the flavor violating processes. And so this box diagram, you can calculate it. What it looks like is something like this. So you get 1 over the mediator mass squared, and then you get 4 couplings like this. And so both real and imaginary parts of these kinds of things are constrained. And then the external quarks can, if they're S and D, you're talking about neutral kaon oscillations, which is extremely well constrained. If one of them is B, then you're talking about B meson oscillations, which are less well constrained, but still pretty well constrained and very consistent with the standard model up to tiny anomalies. So these are the constraints. So there's the delta MK, the difference of the mass of the neutral kaons, and then the B sub D, the B sub S, the difference in the mass, and then the CP violating observables in these 3 sectors. And this is the parameters. So psi K is this product of 4 Yukawas, and then the 1 over mx squared. And these are the bounds, right? So there's some numbers, great, cool. And so then you can make plots of, for example, the couplings, and there you get products of these couplings have to be constrained, so you get these shapes. And so for kaons, it's here, and for B sub D, it's here, and B sub S, kaons is the strongest constraint one, the red one, then B sub D, then B sub S. And so the lesson here, we have a bunch of plots like this on the paper, but the lesson basically is that if you have this Yukawa matrix to be order 1 entries, then you're super dead. You need some of them to be small, or all of them to be small, for you to not be excluded by flavor. And then you can ask about meson decays. So I guess a Feynman diagram would have been helpful here, but I haven't drawn the diagram. But you can have decay. It's the same. It's actually the same diagram, except you turn these things into. You just cut this diagram. Sorry. And so you can get B meson decay, for example, to dark quarks. And so we have, for example, there's a bunch of processes that we came up with where the standard model is somewhere between small and 0. The experimental constraints are strong-ish, but the upcoming experiments, and in particular Bell2 and Kodo2, are going to put much stronger constraints on these decays, and the new physics can generate these kinds of decays. So you can have, for example, B sub D decaying to QQ bar to these emerging jets, or to invisible, or semi-invisible, like this one. So B sub D to pi 0 plus invisible, and similarly K long to invisible, et cetera, et cetera. We also came up with some CP asymmetries, which seem very hard to measure, but in principle, you could be sensitive to the CP phases of these Yukawa couplings. So, for example, you could look at the CP phase of the B sub D decaying to these emerging jets, and how often does the B sub D decay as compared to the B bar sub D. So of course there's no comparable thing in the standard model, but it's proportional to some B physics parameters times some new physics phases. So delta is this new physics phase, while beta is a B physics parameter. And we could talk about various other kinds of asymmetries of this type, and even direct CP violation. So how often does B plus decay to dark pion versus how often does B minus decay to dark pion? So that's a direct CP violation, and it's proportional to this kind of sign of some new physics phases, and there's no equivalent thing in the standard model. All right, so let me conclude. Confining dark sectors are well-motivated extensions of the standard model. Emerging jets are novel and interesting, and LHC experimentalists have started a dedicated search program. Future detectors may also have sensitivity to discovery. The strategies can reach very low cross sections and are sensitive to a broad class of displaced models. Trigger efficiencies at low mass can be improved by adding radiation effects and possibly with new triggers that use machine learning. And there's lots more to do, both from a bottom-up perspective, such as other kinds of dark sectors, and from a top-down perspective, thinking about the symmetries of the flavor structure or symmetries of the gauge structure and unification, etc. So thank you very much.
Yeah, thank you, Daniel, for this nice talk. So it's time for like questions. Yeah, please unmute yourself and yeah.
I have two questions.
Sure.
Okay, thank you for this very nice talk. So my first question is, if the dark pion is LLP but not so long-lived, so should we need to worry about, for example, like a pile-up or underlying event for its emergent jet signature?
Oh yeah, great question. I mean, if it's so we're thinking centimeters or longer, right? I mean, you can look at our plot or the CMS plot. So it sort of stops at 1 millimeter.
Yes.
So yeah, if you're below a millimeter, I would say it's becomes much more difficult. I mean, it's the prompt paired digit search exists. It's tough. And yeah, exactly. So you have to worry about pile up and other things. I think, and that's why the sensitivity sort of craps out at a millimeter. You have to go to much lower masses, which is much higher cross sections, right?
Right.
Yeah, I mean, so there is this nice paper by Pedro Schwaller and others where they interpolate the prompt searches, the missing energy searches, and the searches for displaced stuff to try to cover the whole band. Of course, you don't do quite as well in the prompt case, but they did quantify that.
Okay, good. I will find the paper. My second question is there any other models can also generate this kind of emergent jet instead of the dark QCD model?
That's a good question. I mean, yeah, so if you have any kind of strongly coupled physics, you expect this kind of high multiplicity soft radiation thing. So I mean, yeah, if you're asking about specific models in the literature, I do have a backup slide on this guy. So this paper by Simon Knappen et al. They called it soft bombs, but that's, I think now we call it SOUP. Yeah, soft unclustered energy patterns. And so it's not emerging jet because you don't have they're not angularly clustered, sort of more
Right.
4-pi radiation. So that you can certainly do, but I mean, I think sort of strong dynamics will give you high multiplicity. I don't know if you can do it in a weakly coupled model, if that's what you're at. Yeah.
Okay, thank you.
Yep, thanks.
So I have a question.
Sure, please.
And so in the end of your talk, you introduced the indirect search of the CP phase in the dark sector. So is it necessary for the generation of asymmetry?
Good question. So obviously there has to be some CP violation for the generation of some asymmetry, but I don't think it has to be in this Yukawa coupling, right? So the generation of the asymmetry story is that you have some other physics coupled to this phi that causes the asymmetry. So then when the phi decays, the asymmetry is already imprinted in the phi, and so there doesn't have to be any additional CP violation there. So I guess the answer to your question is no. But there's also no reason to expect that the CP phases are small.
Okay. Yeah, thanks.
Yeah, good question.
Yes, there any other questions? Yeah, actually I have one, like in the page 29, you show the distribution from the CMS searching for this emerging jet. So I'm wondering if this distribution sensitive to the dynamics in the hidden sector at a higher energy, or it's fully determined by the low energy effective theory?
Oh, sorry, what do you mean by the energy at high, like
Like after the theory confined, like the dark quark combined to the dark pion. So all this distribution determined by the decay constant and also the mass. Is also the distribution sensitive to other parameters in the hidden sector?
Yeah, that's a good question. I don't know. I think these are chosen to be relatively insensitive to that, but and I'm sure they studied it, but they did not publish that. I mean, there must be some sensitivity, right, to the showering, right? Because if you have higher, if you shower more, you have higher multiplicity and softer dark pions, you get a different answer here, right? So the energy distribution of the dark pions is going to be imprinted.
Okay.
And what they did is they studied this in Pythia. So, you know, what you can vary some things in Pythia, but not a lot of things, right? The showering in Pythia is designed to be standard model like, QCD like.
Okay, yeah.
And so
Yeah,
certainly,
so that yeah, that's related to my second question. Is this sensitive to the how we model the showering, the dark showering?
Yeah, exactly. So hopefully not too much, but I don't know how to prove that, right? So what you can prove is that if you vary the parameters in Pythia, it doesn't change the answer too much. And I'm sure they did that, and we did that to some extent, and it reasonably works for these kinds of variables. But yeah, I think that's only a very incomplete answer to that question, which I don't know how to answer it better.
Okay, thank you. And in the page 59, you showed you talk about the machine learning things. So what's the variable you use as input for training those things?
Good. So you first we cluster the jets, and then the variables are the number of hits inside the jet cone at each layer.
Mm-hmm. It's
So
just this hit, the hits.
Yeah, just counts of hits. Yeah.
Okay. Good. Thank you.
Yeah. Thank you.
Is there any other questions from the audience? Yeah. Okay. If no, let's thank the speakers again and for this nice talk. And yeah, so if you have the opportunity, please visit us and in Nanjing.
Absolutely.
And I hope I can also have the opportunity to visit Carlton again.
Yeah, we definitely would love
friends.
to have you back. And yeah,
yeah,
great. Thank you for everyone for connecting and for the very nice questions.
Yeah. Okay. Yeah. By the way, can you send me the slides so we can also post it
Sure.
on our website?
Sure, I will.
Okay.
I will do.
Okay.
I just got to generate.
Thank
the PDF.
you.
Yeah. Okay. Thanks.
Yeah.
See you later.
See you.
Thank you. Bye-bye.
Yeah. See you all.